morning, everyone, and welcome. I'm Anup Divakaran, a sales manager with Digitoad Technologies, and I'll be your host for today's session. Now, thank you, everyone, for joining the webinar on driving 6G innovation with mmWave, Testbeds, and RIS. This webinar is hosted by Digitoad, TMY Tech, and NI. We will have three speakers with us today. We have Rohit Prajapati, who's the Managing Director at Digitoad Technologies. He will share insights on wireless technologies and market trends, followed by Siddharth Dhawan. He is an application engineer at NI who will provide us an introduction to USRP and an overview of 6G technology. At last, we will have Vincent Lee, an account manager at TMY Tech, who will present on 6G testbed integration, real-world use cases, and a live demo. We'll also conclude with a 10-minute Q&A session to address your questions. So hold on to your questions. We will have a session at the end to address all of it. You would also be able to email us your questions that we are not able to take during this 1 hour window. Now, to get us started, I'd like to hand it over to Rohit Prajapati to share his thoughts and insights.
Hey, thanks, Anup. Hope I'm audible. Okay, let me share my screen. I have shared my screen, and I hope that my screen is visible to all the participants. In case if during the presentation, if there is a slight discontinuity in the slides or changing of the slides, please let me know. Okay, warm good morning to all the participants. To Prajapati, Managing Director of Digitoad Technologies. I founded Digitoad in 2018 and facilitating these technologies to the academics, especially in India, ecosystem in India. Digitoad Technologies, we are the leading provider of industrial, academic, and research solutions across test and measurement, 5G, 6G wireless research, and AI-driven IoT and embedded ecosystem. We largely work with academics and enabling them with tools and technology for enhanced teaching and research. We engage with engineering institutes for academic teaching and research engineering institutes across India. We do a lot of program which involves us to deliver high quality immersive training on latest technologies, which again involves certificates, close to 25 plus MOUs we have signed till date with different engineering colleges across India. We are also instrumental in setting up skilling centers. When it comes to key solutions, we have solutions on automated test and measurement. We work a lot on AI and machine learning based applications, FPGA and semiconductors, 5G and 6G wireless research, which today's webinar is all about. Names from industry to enable technologies across academics involves ST, Digiland, NI, Mantis Wave, Mix, R&D institutes. This is the most important moment to explore, prototype, and advance in 6G technologies. Academics focusing on enhanced 6G research outcomes and the industry looking for early adoption. The role of Digitoad only expands into bridging the gap and accelerating the 6G research by bringing the stakeholders from the industry, such as NI and TMY Tech. Together, we not only focus on handholding initiatives, this also allows us to create a testbed that transforms 6G research into industries. We have witnessed significant transformation over the past few years, and this has been from first generation to the fifth generation in the telecommunication. Fifth generation had something to evolve and improve. But in case of the evolution from 5th generation to 6th generation, it is most about how connectivity and network will embed intelligence. So 5G was focused mostly on enabling ultra reliable, low latency communication, massive IoT communication, and private networks. So 5G helped us lay the foundation for smart factory, but as it's not only about massive capacity or higher speeds, but also about embedding intelligence into the network itself. So today we are talking about AI native networks that can self-optimize sub-gigahertz, and we have networks integrating satellites and drones and experiencing truly immersive communication and digital twins. For researchers and opportunity and laying the foundation for future industries, create intelligent, adaptive, and human-centric networks. So as we have seen in the previous slide, that 6G is here to lay the foundation for futuristic. This is being driven by 3 key factors: the what, the market focus, the how, and the applications, the why. So enabling technologies are built and beyond. Low latency for mission critical tasks. Now, when from government bodies and research being, additionally industry readiness for early adoption, we can only imagine how strong the push accelerates 6G research. Now, 6G will enable us use cases which were once thought impossible. We can think VR experiences, autonomous mobility on and in the air, next generation health, fully connected and intelligent factories. So together, these factors are not a vision of 6G, but they are creating a demand for testbeds and prototyping platforms that allow these technological applications to be visions. Now, in order to move from concept to reality, what is required? So the most important piece is testbed rapid prototyping platforms. With NI's USR radios, researchers get a highly flexible and architecture that can adapt to different spectrum bands and protocols. Now, when we combine this with TMY-Tech's mmWave solutions and dynamic reconfigurable intelligent surfaces, we unlock the ability to challenges of 6G, right? This testbeds act as a bridge between elements. Now, for academics, what does it mean? It means students just try quickly, validate the results, and even contribute towards global standards and IP development, which is very important for Make in India. So in short, testbeds are not just tools, they are enablers of innovation. They allow universities and R&D institutes to go from simulation to scalable industry solution. So last, we look at the India's goal, but to take leadership in shaping it globally. So for again, opens up tremendous opportunities. So at Digitoad, we believe that this is the time for universities to align with the industry to 6G research. By working with NI and TMY-Tech, we can help build India the ecosystem that it needs by connecting industry adoption. Now, if we get this right, India won't just participate in 6G, but we can actually help shape the global 6G landscape. From my end, next I would like to invite Siddhant from NI to discuss more on the core technology in 6G research. Over to you, Siddhant. Thanks.
Yeah, thanks Rohit for the great introduction. So hi everyone, I'm Siddhant from National Instruments. So I'll quickly share my screen and go towards the slides. So hi everyone, I'm Siddhant Dhawan from National Instruments. I'm wireless expert here at NI, which is now part of Emerson. So this is a little background about me. So I have around 7+ years of experience in RF and microwave. and I've worked as an R&D engineer, testing engineer, as well as an application engineer. Currently is my role. Now I have expertise in technologies right from aerospace and defense to mobile communication like 4G, 5G, and the latest trends which are ongoing in 6G like ISEC and NTN. Then towards hardware side, I have expertise in software-defined radios, vector signal transceivers, and towards software side, I have expertise in open source tool chain. Now at NI, I'm currently working with majorly with academic customers and where the research comes from. So I'll be now going through the slides. So whenever we talk about 6G, the first question which comes into anybody's mind is why we actually require 6G. So there are certain reasons why we actually require 6G. First of all, we are talking about the spectrum expansion in 6G. So as we are all aware that along with the existing spectrum in 4G and 5G, we are now concentrating on new spectrum, which is FR3, which is somewhere in between FR1 and FR2, as well as sub-terahertz, which is like 100 gigs to 300 gigs. Now 6G will cater new applications like NTN and ISEC, which are high-speed applications. And along with that, we are aiming at network optimization. And all together, when clubbed with AI/ML, so then 6G will become a game changer in mobile communication. Now, these are the latest trends as per 3GPP. So we can expect the first spec of 6G, which will be release 20, to be available somewhere in the starting of 2027. And as we are all aware that the first kickoff meeting of 6G 3GPP workgroup meeting happened in Bangalore in August, which was a kickoff meeting for 6G. Now, release 21 will be much more matured spec of 6G, and it will be somewhere available around end of 2028. Now, as we all know that in 6G, we are expanding the spectrum in two ways. One is along the FR3 region, which we call upper midband, and one in sub-terahertz range, which is 100 gigs to 300 gigs. Now, I would like to demonstrate where NI stand when we talk about 6G. So these are the major scenarios which we are concentrating when 6G is concerned. So for example, we are heavily investing and we are heavily concentrating on AI/ML stuff as far as 6G is concerned. Then ISEC, integrated sensing and communication, RIS, sub-terahertz solution, and OAI and SRS based 5G end-to-end system. I'll quickly go through all of these. So I've created a very brief slide about all the POCs and demos that we have. So the top left-hand side you can see is an RF data recording API. It is actually the API which we use in all of our AI/ML based solutions. So we have made this API in collaboration with Northeastern University. And basically, this API captures the RF data, raw RF data, and add a metadata to it and convert it into SIGMA format. Now, the beauty of this API is it can be used to train the AI model, as well as it can be used for implementing the application where we use the pre-trained AI model. Similarly, our USRPs are well capable of OAI and SRS-based 5G SA end-to-end system. Now, another application in 6G which we are talking about is integrated sensing and communication. And you can see here delay Doppler map. So we have implemented it with the help of our USRP. On the bottom row, you can see AI-based spectrum sensing. It is in great demand, whether it is academic or whether it is aerospace and defense. So here, basically, we are capturing the spectrum, and then we are detecting this spectrum is belonging to which technology, whether it is a Wi-Fi signal or 4G signal or 5G signal or it is a radar signal. Similarly, we have another AI/ML based POC, which is AI/ML neural receiver. Here we have actually implemented channel estimation using AI/ML algorithms in uplink. And similarly, we have solution based on RIS. So RIS will be discussed more by TM by Tech, because here is the area we collaborate with TM by Tech, and our USRP with TM by Tech's solution like RIS and up-down converter will be a great fit in this area. Now, I would like to demonstrate where NI do business. So NI has business in two variants. So first is the prototyping business, where our USRP is a good fit. And second business is actually a validation business, where our PXI platform like VST oscilloscope will be a good fit. But since this webinar is more towards prototyping business, so I'll be concentrating more towards USRP. So why we actually require SDR? So left-hand side, you can see there are some hard-coded radios, and on the right-hand side, you can see commercial on-the-shelf radios. We require something in between, which we can change according to the software for new research, and where we can have access to FPGA as well as RF front end. Here, actually, our software defined radios, which we call USRPs, is a great fit. So which provide RF front ends as well as FPGA for DSP. So what use cases you can solve with the help of our USRPs? So I've categorized these use cases in 4 categories. One is academic research. Our USRP is a great fit in academic research and currently being used widely in academics. Firstly, like in waveform, right from the waveform prototyping, 5G SRS and OA system, NTN research, till and a new application which is coming these days, which is a security of communication between medical devices. So USRP is a great fit for that. Secondly, for aerospace and defense industry, it is a great fit for drone and anti-drone technologies, direction finding, cognitive radio and adaptive radios. Similarly, now as we are talking about 6G, AI and ML will play a pivotal role in 6G. So we have AI ML based channel estimation, AI ML based spectrum monitoring and sensing. Similarly, in the area of radio and astronomy, we have radio astronomy, GPS receivers and simulators, satellite based communication research, which can be done on our SDRs. So this will be the basic architecture of SDR. So as you can all see, on the right hand side, we have an RF front end. So we receive the RF signal and do all the down conversions and everything, and then it is passed through ADC and DACs. Now after that, you can see there is an FPGA into the chain. So some of the SDRs have FPGA accessible, and so basically you can do host level programming as well on our SDRs, and you can do FPGA level programming as well. So for example, you want to implement or validate any protocol, so our FPGA is well available. FPGA inside USRP is well available for that. On the other hand, if you want to do some host level programming with some normal CPU or maybe having a GPU, then you can do host level programming as well. So this is a portfolio of our SDRs, and our SDRs are categorized into various categories, right from the bus series, so where bus stands for USB bus, then we have embedded series, and then we have network series, and then we have X series USRP with our X410 and X440 with the latest one. A more simplified slide I would like to show here is the one. So basically our USRP supports LabVIEW based environment, even the open source environment, and even MATLAB as well. And it depends on which variant you are selecting. So like X series, X410 and X440 USRPs are the latest one, and we'll be showing our OA demo using X410. So basically it supports LabVIEW as well as open source like RFNOC and GNU Radio. And its FPGA is well accessible if you want to implement any digital signal processing algorithms. Now, winding up about the hardware side, we have something good on the software side as well. So as most of you must be doing the physical layer research. So when we talk about 6G, the major change which will come will be first in the physical layer. So we have something called modulation toolkit, which actually caters source coding, channel coding, and modulation. So if you are researching, let's say on new modulation, the one way is to start it from scratch. Now it will be a very tedious project. I mean, if you start from very scratch. Now, what modulation toolkit helps you, we have already made the standard modulation, channel coding algorithm, and source coding already available. So it provides you a starting point, and on top you can build that. The beauty of this is you can even access it with LabVIEW as well as through open source softwares like Python, because its APIs are well exposed. And we even provide the utilities to analyze your research, such as IQ diagram and I diagrams. So I would now like to put little light on our latest event that has happened, NI Days in Bangalore in July. So this was the booth that we have set for wireless. So on the right hand side, you can see on the top, it is AI-based spectrum sensing that we have showcased through our USRP. Below is integrated sensing and communication that we have showcased, again with the help of USRPs. On the left, it is 5G end-to-end system using OA stack. It is again implemented using our X410. So these are some of the institutes that we are already working with, where we have either Center of Excellence, Wireless Prototyping Lab, or Advanced Wireless Teaching Labs. These are some of the application notes which are available on NI website. So this slide will be forwarded to you, everyone, and feel free to reach out to me even after the presentation as well if you have any doubt. Thank you so much. This was all from my side. So now I would like to hand over to Vincent to move towards little bit towards TMY tech products. Over to you, Vincent.
Hi everyone, my name is Vincent Lee from TMY Tech. So, well, good morning or good afternoon, depends on where you are coming from. And we are very happy today to invite all of you to enjoy our webinar. And the main topic of the webinar today is driving 6G innovation with mmWave testbeds and also, well, of course, the RIS. So hopefully after the meeting, you are able to learn something after this webinar. And today we want to show you how our millimeter wave testbed can be helpful, can be beneficial for your future wireless research. So, well, of course, you will probably think why we want to arrange this webinar today. It's all because of AI, and you probably use AI every day. You want ChatGPT to help you for example, if you want to look for a restaurant, or if you want ChatGPT to create a very nice video, some nice pictures for you. And no matter how, you will always create a data. So many people use ChatGPT every day. That will increase, that will also create a huge amount of data between multiple devices. And now you also have more and more devices needs to be connected every day. For example, from the base station to your mobile phone, and then from mobile phone to other mobile phones. So there are so many devices needs to be connected every day. So of course, and also much big data needs to be transferred. So then we would say the current 4G LTE framework or the 5G FR1 system is not enough because it cannot handle a huge amount of data. So you can see here, the global connection traffic is expected to increase a lot in the future years. So then, of course, we need much more reliable connections network in the future. So that's why, well, 6G. So then you can take a look here. This is the network system. We usually use a term. It's called ubiquitous. So, for example, if you are living in a very center area in a city center with many people living in a very small, dense area, and that there will be so many devices needs to be connected every day. And also, if you watch videos, and also, well, if you use ChatGPT and this area, you need a much more network system that will be able to handle a huge amount of data. So of course here FR2, because a very dense area, but it's very small. So the FR2 network system you will be able to handle. But if you live in the middle between the city center and also the rural area, we probably use the FR3. So the FR3 is the band between FR1 and FR2. Of course, you know about it, and you can still handle a huge amount of data, but compared to FR1, then compared to FR2, it has much more better signal coverage because the frequency is a little bit lower. So this is a place you can, of course, use FR3. And then if you are living in the rural area, which is the outer circle, and this is a place you can still use FR1 because you are very far away from the city center and there are not so many people living here. So in this area, you can use FR1 because FR1 has better signal coverage. So, well, this is how the future communication system looks like. And then if you are living in a very remote area, so for example, in the mountains, and usually like before you don't have any network connection, so then you can use the satellites. So the satellite communication, you of course you all heard about Starlink. This is how you can use. This is the right place. You can use the ground terminal, and then your laptop or mobile phone can connect to the user terminal, and then the user terminal it will connect to the satellites. So you can of course enjoy the internet every moment. So the whole system is going to be look like this one. So just a very quick preview of the future 6G roadmap. So you can see you have the satellites, no matter it's LEO, MEO, or GEO, and then you can of course use the satellites. It really depends on the applications, but with the satellites, you can use the satellites to connect the unconnected area. And then in the city center, you can see the base stations, and also you can see the RIS. So, well, today we want to show you how our 6G system can be helpful for the research and also for academic purposes. Just a very brief introduction of our company. So you can see here, TMY Tech is been in a millimeter wave market more than 10 years. So we primarily focus on FR2 and also FR3 bands. So we have a different frequency converters, antennas, which are designed for FR2 and also FR3 bands. The headquarters is in Taipei, Taiwan, and we have a different offices in different countries. So you can see here, this is our product solution portfolio, and today we are going to introduce our millimeter wave instruments. So on your left hand side, you can see multiple, we call the boxes. Well, because the main topic we want to share today is if you are a professor from universities or if you are engineer from in wireless companies, you may struggle. One thing is you don't have any proper hardware devices to conduct your 6G research. No matter if you are doing beam tracking algorithm or if you are designing the RIS, but you don't have any proper hardware devices. So this is what we see the challenges in the market, and this is the problem we want to solve. So today we are going to present our solution for 6G and also even for 5G research. So on your right hand side, you can also see we are companies designing different types of phase arrays, and these are the phase arrays modules. They are much more for the commercial purposes. So that's why we also have other products which are ready to be used, and these are the commercial products. But we are not focused today, so we will present our boxes. So you can see here the solution you can see from the left is our FR2 and also FR3 solution. So you can see we have the beamformer, we have the frequency converter, and then you can also see the OEI box is from other companies, from our partner company called OB Smart. So today we are going to show you our FR2 and also FR3 ready platform for beamforming, beam tracking, research, and also based on NISDR, or you call the USRP system. And the product, the solution in the middle is the RIS. It's called Reconfiguring Intelligent Surface. This is a very new and also very hot topic in the past years. So the first 6G testbed is this one. So this is our frequency converter, and we call FR3 converter. So it's an up and down converter. The frequency coverage is from 6 to 30 gigahertz. The solution here is the testbed we develop and also we test with NI-USRP X440. So you can see X440, it has multiple channels. So here you can see we use 4 transmitters, 4 receivers, and then we up and down convert from sub-6 gigahertz to radio frequencies. So for example, we up convert from 3 gigahertz to 15 gigahertz, and then we use all the channels, and we do also down convert because this is a frequency converter. It's a bidirectional system. So the same frequency converter, you can either do up and down conversion. So here, the highlight is after the up and down converters, we can still keep a very nice phase. So you can see the phase deviation is very, very minor after frequency up and down conversions. And also, we use multiple channels. We up and down convert multiple channels. So you can see every single channel, and also between different frequency converters, we can also synchronize all the frequency converters very well. So this is a frequency converter. You have an internal and also external local oscillator, which can be synchronized between devices. So this is one thing. This is a very nice, powerful platform for 6G research. It can be used also even for defense and also satellites applications. So this is the first thing we are introducing here. And then if you are also doing FR3 testbed, and you can see here we also have the frequency converter with our home antennas. If you want to transmit the signal from A to B, and if you want to do some over-the-air test, this is the frequency converter you can use for FR3 bands. So the frequency converter, again, you can cover from 6 to 30 gigahertz. So you can use different types of USRP system. So for example, you have the X410, and if you have also X310 or 2974, our frequency converter is compatible with different kinds of different kinds of USRP system. So this is also a platform for you if you want to do over-the-air test. Then the next solution is the RIS. So RIS stands for Reconfigurable Intelligent Surface. Well, this is why we need the RIS. So you can see if you have the signal from the left and it's FR2 signal or FR3, the signal is going all the way into the room, but the millimeter wave signal is very sensitive. So you cannot penetrate any objects. And if you are here, so you can see the blue area is the cold zone or the dead zone. Is here you don't have any connection because it's FR2 or FR3. So we need a device which we can redirect the signal. So that's why many people talk about the RIS. It's this way. The signal will be pointing to the RIS, and then it will be redirected to the area. So you can also control the reflection beam to any directions as you wish. So then the RIS here, we have different frequencies. So from 3.5, 4.7, and also 28 gigahertz. The RIS is based on the pin diodes. So then this is how you can control the RIS. You can control all the phase shifter of each element. And this is a RIS. So you can see we have the RIS and also the controller. It's a different items because with the controller and also the RIS into different items. Here, the good thing is here. The RIS, each controller, it can control up to 4 different RIS. So you can see here, each controller, you can control, for example, 2 RIS of 4.7 gigahertz, and also the other 2 RIS of 28 gigahertz. So here you have the freedom to extend the RIS from 1 RIS and then to 4 different RIS. So you can also combine all the RIS together into one bigger RIS. So for example, the RIS of 28 gigahertz, you have a 32 by 32 antenna elements, but then once you combine all the items together, it becomes a larger RIS, which is 64 plus 64. So this is a very nice and also very it's also a scalable structure of the RIS. Okay.
As we move towards 6G, dynamic RIS is redefining how signals travel. With active control, each RIS element can precisely reflect, steer, or focus millimeter wave signals. Let's take a closer look. We set up a typical L-shaped corner reflection scenario. At the transmitter side, VBox 1 sends RF signals. The UD Box 5G handles up conversion to millimeter wave, while the NIPXI VST system generates the signal. The signal hits the RIS, which is now in a 2x2 array mode, extending both range and coverage. It then reflects toward VBox light, down converted again by the UD Box 5G, and analyzed by the PXI VST. Here, we can clearly see performance through real-time data. With WebTLK, we can combine RIS tiles into larger arrays based on distance and easily adjust the reflection angle. Now we switch to a 1x2 array. This shows how different setups impact signal behavior and how flexible dynamic RIS can be. RIS offers hybrid band advantages, enabling seamless switching between FR1 and FR2 bands. With just one controller, users can easily reconfigure the system for different frequency ranges. Dynamic RIS unlocks a software-defined environment, enabling more efficient and controllable millimeter wave communication. Remember to subscribe, like, and ring the bell.
Okay, so this is our RIS solution. So in the previous slides, we introduced our FR3 frequency converter. So, and also our RIS, they are much more for the 6G research. But here, one thing we are going to introduce is our FR2 testbed. So probably some of you have probably already heard about our FR2 testbed, because this is a solution we have been delivering to many universities in different countries. So it's been very helpful for many professors. So they use our FR2 testbed for their research. So the FR2 testbed, you can see here. Here you have 2 front-end modules. So you can see the golden phase arrays. On your right-hand side is our VBox 1. So this is a one with 4x4 antenna array. You can do horizontal and also vertical beam steering. On your left-hand side is our VBox Lite, which is the lighter version of the VBox 1. So the VBox 1, you have 16 RF channels. The VBox Lite, you have 4 channels. So the whole system here is for you to simulate the communication system between 5G FR2 base station and also the 5G FR2 mobile phone. And here, the box on top of the big PXI chassis is the USRP X410 again. And on top of the USRP is our FR2 frequency converter. So we have 2 types of frequency converter. One is FR2 frequency converter. Here we are presenting here, but we also have the FR3 frequency converter. You can see in the previous slides. So our frequency converter with 2 kinds, it can cover from 6 to 44 gigahertz because FR2 and then FR3. So the whole system here again is for you to simulate a communication system between 5G FR2 base station and then FR2 mobile phone. So here you can see another box, which is the OAI box. So the OAI box stands for Open Air Interface. And this is a solution we create with a Portuguese company called OB Smart. So the OAI box, it's actually a 5G core network. So you have all the software stack running on the box. And it's also a plug and play box because if you know OAI system, probably some people they are struggling with the OAI architecture because everything is open, so you don't have anything in the market ready to be used. So this is the OAI box ready. The OAI box is something ready to use, and then you can program your own OAI architecture, and then everything is programmable. So you can run all the software stack based on the OAI box. So again, you always need the SDR system and also our frequency converter and also the beamformers. So you can see the whole structure here. So the 5G FR2 OAI reference architecture is you have the core network 5G OAI box from OB Smart, and then you have USR BX410 from NI, and here you have the frequency FR2 frequency converter and also B box from TMI Tag. So with three boxes together, it's actually a complete RF chain. It's actually in a 5G FR2 base station. So you can actually use multiple different kinds of UE. You can use COTS UE from the market. And now we are still working with OB Smart and also NI because hopefully we can use the other FR2 commercial mobile phone from the market. So such as iPhone 16 or 17 or Samsung S20, 21, 22. So this is the next step we are going to work on. So a very quick video. This is the research we did with HHI Fraunhofer from Germany. So this video is going to show you how you can use the OAI FR2 platform for your OAI research.
In this demo, our base station runs the OAI protocol stack on the OAI box from OB Smart. The R frontend includes USRP X410 from National Instruments, along with TMY tags, up-down converter, and two 16-element analog beamforming arrays operating at the carrier frequency of 28 GHz. On the UE side, we use the FR2-enabled 3GPP Release 16 compliant Quectel modem with two antenna ports. This configuration allows us to achieve multiplexing of two spatial streams, resulting in a significant increase in throughput compared to a single antenna setup. This marks the world's first open source 5G standalone FR2 MIMO demonstrator, setting a new milestone in the Open Air Interface Software Alliance. With this work, we extend our research capability in the FR2 band, allowing us to exploit larger available bandwidth and explore new opportunities for integrating sensing and communication, or ISAC in short.
Right. So hopefully this is a video for you. You can understand how the FR2 OAI solution can be helpful for OAI research. Okay. So, and then again with the RIS, with OAI, this is how the next research platform we are going to work on. So with the OAI GNOB, with the OAI UE, then this is our RIS. So we also wanted to control the RIS. from the OAI box. Okay, so well, some application notes to understand how you can also use these platforms. Okay, so this is the bin tracking RIS algorithm video we show in the past conferences. So you can see you have the RIS in the middle, and on your right hand side is the VBox one, and sorry, on your left hand side is the VBox one, on your right hand side is the VBox Lite. So now here we generate a signal from the VBox as a transmitter, and then pointing to the RIS, and then the signal is being redirected to the receiver. So the main idea of the demo here is no matter how you move the receiver or transmitter, you can still keep a very nice signal because we developed a very, very simple algorithm. So how it works is once the receiving power is below a certain level, and then the API, so the bin tracking code, it will trigger all the devices to rescan the beam again, trying to find where the signal is coming from. So the beam, it will keep scanning until it finds a signal from a certain direction, and then all the beams they will point to the same direction. So and then once all the beams they are well aligned, and then they will lock each other. So this is a demo we want to show you as inspiration if you are going to develop your own bin tracking algorithm. So this is how you can use our devices. Then on top of our devices, you can verify your own bin tracking algorithm. So this is the main purpose of the demo here. Okay, well, so the last page is we are now designing our new system, which is 4x4 MIMO testbed. Again, it's based on the NI-USRP. So the new device is 8x8 antenna array dual polarization. This is a device including the phase array, frequency conversion, all into one box. So the box, this one, you can use for MIMO research because you have all the antenna and also the frequency converter into a very compact box. So this is a box you can connect directly to the to the NI-USRP because you don't need a frequency converter anymore. You don't need a frequency converter anymore because it's already been integrated. So this is a solution we are still designing, but that should be ready by the very early. So if you want to know more about this 4x4 MIMO testbed, well, it can be also extended to 8x8 MIMO testbed. If you want to know more about it, then of course you can email us. You can send us an email, so we will be able to share you with a little bit more information.
From here, we take that and we take the max average over a set period of time, in this case 5 milliseconds, and we take hundreds of those over a period of time to create a histogram. So the histogram will show us the absolute max of all these signals. So we're looking at the absolute max worst case over large chunks of time, in this case being about a 20th of a second. And what we should see, and what we're seeing here, is a very tight phase coherence. If you zoomed in on this, you're going to see that it's about 0.003 radians, and the center frequency here is about 75 megahertz. So that's a fairly small deviation from the overall center frequency that we have there. In terms of what the TMY Tech devices are doing is they take the IF here at 75 megahertz. We're up converting to 14 gigahertz, and then down converting the same thing. So they're just in the loop to show that we can do this up and down conversion. And then they're going to add some noise to the overall system. And that's what we see here, is this overall noise being added. That's normal because of phase noise in the added system compared with what's coming through the paths. but it's still very tight phase coherence over the overall system. As you can see, the magnitude is changing somewhat here and there, but that's not as large of a concern because the phase coherence is native to the device. The magnitude will have to get worked out either way. And that's the broader concept of the overall demo.
Hello everyone, this is a new demonstration from TMY Tech. This application is about the fast coherency application with radar. So we use NI-X440 to generate 3.255 GHz and use TMY Tech UD630 to up converter to 11.4 GHz. Use our web TLK like this. Then it allowed we can use really millimeter wave horn antenna to do OTA testing. So this is a testing setup allowed user can do real radar application in real in OTA environment. Thank you.
Now let's examine how the signal is transmitted and enhanced. The G-Node B generates a high-quality 5G signal through the test bed include B-Box 1 and UD-Box and NI-X410 and transmits it to the X-rifle reflector for the first reflection. At the X-rifle reflector, the incident angle is set to 30 degrees and the reflection angle is set to 60 degrees, ensuring the signal is accurately directed toward the dynamic RIS. The signal then enters dynamic RIS for the second reflection with an incident angle of 0 degrees and a reflection angle of 60 degrees, successfully transmitting to the first FR2 COTS UE, completing the registration and connection process. The reflection angle of the dynamic RIS is controlled using TMY Tech's WebTLK online software. WebTLK features an industry-first intuitive visualized control interface, allowing users to easily adjust the beam direction and reflection angle in real time, making RIS configuration more flexible and efficient. After the first reflection is completed, we use WebTLK to reconfigure the RIS to direct the signal toward the other UE device. Through an intelligent adjustment mechanism, the RIS alternates the signal reflection between two different directions, ensuring that both FR2 COTS UE positioned in different locations successfully receive the signal, register, and establish a connection. Our test results show that in the NRFR2 band under a SISO configuration, the system achieves a throughput of up to 300 megabits per second, demonstrating outstanding network performance.
Let's take a closer look. We set up a typical L-shaped corner reflection scenario. At the transmitter side, B-Box 1 sends RF signals. The UD-Box 5G handles up conversion to millimeter wave, while the NIPXI VST system generates the signal. The signal hits the RIS, which is now in a 2x2 array mode, extending both range and coverage. It then reflects toward B-Box light, down converted again by the UD-Box 5G, and analyzed by the PXI VST. Here, we can clearly see performance through real-time data. With WebTLK, we can combine RIS tiles into larger arrays based on distance and easily adjust the reflection angle. Now we switch to a 1x2 array. This shows how different setups impact signal behavior and how flexible dynamic RIS can be. RIS offers hybrid band advantages, enabling seamless switching between FR1 and FR2 bands. With just one controller, users can easily reconfigure the system for different frequency ranges. Dynamic RIS unlocks a software-defined environment, enabling more efficient and controllable millimeter wave communication.
Okay, so right now is the Q&A section. If you have any questions, then feel free to ask here, so we will answer.
Hello, can you hear me? Yeah, hi everyone. I think now it's the time to have live demonstration of OAI setup. So I'll quickly go through the basics of OAI first. As a normal architecture, I quickly share my screen and explain a block diagram out of it. And then TMY Tech team can do a live demonstration. So basically, OAI is an open source stack built by Eurocom, and it is an open source stack, so anybody can provide any changes or anything and suggest anything. So how it works? So we have a core network which is running in the form of Dockerized images. So these Docker images are nothing but individual elements of the core network. Once this core network is ready, then we have a Gnode B, which is running on some CPU or server, and then where whole of the physical layer processing is happening, and then it is up converted and being sent. So here the USRP comes into picture, where we are up converting and sending it over to the air. Now at the UE end, you can have three options. One, USRP itself can act as a UE, and you need to have all the SIM information into the config files. Secondly, you can have commercial on-the-shelf UE with a specialized SIM which comes, and you can connect it to the OAI network. And third is kind of PCB kind of modules with a specialized SIM, where you can connect it to the OAI network. Now I would like to hand it over to TMY Tech team to discuss more in detail that how we are converting and taking this towards FR2 OAI. Over to you, Alex.
太大。Hello.
Yeah, you're audible, Alex.
Hello, everyone. I'm Alex, a field application engineer from Tier 1 Tech. Okay, today we are introducing our FR2 solution for OAI integration. So now you can see the setup on the desk. We have an OAI box here and a beamformer. Then we also have an X440 and a UD5G. Now, after thanks for Eden's introduction. So, X440 will support, X410 will support the core network, and it will generate the FR2 signal. Then we can use our UD up and down converter to upgrade 28 gigahertz for real millimeter wave frequency. Then after we up converted to 28 gigahertz. Then we use a beamformer to transmit and receive signal from BBox. BBox is a beamformer can direction different angle. Then we use a RIS to reflection different signal from here to our end user device. We call it COS UE. So this is total setup is from terminal to user end, and we also have a RIS control tool to control each element, because some guests are also asking how to control the RIS. So this is a tool we control the RIS system. And if you want to know more, you can visit our website. Okay, thank you. And let's move on to Q&A section.
All right, we have a question from Farhana. How do you deal with beam alignment and tracking in a testbed when user equipment is mobile? All right, Vincent, can you take this?
Hey, so this is Vincent from TMI Tech. And regarding the beam alignment and tracking system if the user equipment is mobile. This is actually the topic we are also working with OB Smart and also NI based on OAI interface. So the concept is going to be when the user is actually moving and when the receiving power is below a certain level, and then the beam, they should be able to start rescan until it locates the user equipment. Then the signal, it will lock this direction. Yeah.
All right, Farana, I hope that answers your question. Do we have any more questions from the audience? Okay, you should know that if you do not have any questions now, if anything comes up later, you can always email us. You can email it to sales@digitoad.com, and we'd be happy to answer your questions. All right, I'll give it a few.
Sorry, just one last thing, because we are now also going to join IMC. So if you want to see any live demo, please just stop by our booth. Then you can see all the live demo we are presenting today.
Thank you, Vincent. I'd like to touch base on that in a little more detail. So that's happening between 8th to 11th of October at Yashobhoomi in Delhi. So if you'd like to experience these solutions firsthand, do visit us at our booth. You would, of course, get emails from us with details of the booth and where to meet us. And thank you, everyone, for being a part of today's webinar on driving 6G innovation with mmWave, Testbeds, and RIS. And I'd like to give out a big thanks to our speakers, Rohit, Siddhant, and Vincent, for their valuable insights and demos. And we, of course, appreciate your time and participation, and we look forward to connecting with you again soon. Thank you, everyone.
Remember to subscribe, like, and ring the bell.